But because they are well known, and this being the big advantage, they are operating with well-known problems, they're also highly predictable. And that's probably one of the strongest advantages of using this sort of system. They are highly predictable. Not only are the models likely to behave in predictable ways and give predictable outcomes, but the data scientists are also able to give estimates for the durations of their work. That means they can say, in order to integrate this piece of machine learning, it is likely to take me a certain amount of time. Or indeed, if they want to start interpreting those outputs or tweaking or changing the way the model works, then they're able to give more accurate estimates, or at least relative estimates that we as Agilists are able to use to help understand how much work a data scientist has to get through, and fundamentally when a given piece of work is likely to be done. And this means that Scrum works. That degree of predictability, that degree of capability to estimate, means that everything that we do with Agile Scrum actually fits very well. We have a backlog of work. That backlog can be sliced down. The team can give relative estimations. We can have vertical stories that span all parts of the system, from the front end through to the back end, through to APIs, through to the data science. We're actually able to develop and build on user stories and deliver those. And that means we can also do sprint planning, and we can estimate how much is going to be done and use burn down charts as well. We have regular collaboration and the regular demonstration of value to our customer. Scrum works under these circumstances, and it's actually a very natural fit. Now, that being said, there are a couple of key elements that we need to be very aware of and to bear in mind. First off, models need data. It sounds fairly obvious, but I've worked on a vast number of projects where the where the data just wasn't available, or it didn't become available until quite late on. And the data scientists will need a data phase to analyze that incoming data so they can organize it into such a way that the model can use. If you don't have the data, you can't organize it. If you can't organize it, you can't feed your model. If you can't feed your model, you will not actually have a model that can interpret an output. And the next thing we need to be aware of is what our agreed accuracy targets are. Now, the accuracy targets we'll talk about a little bit later, but fundamentally it is about how well the model performs. So once we've got our data, once we've got our model, we can merge those two together, and we can set the model up to be able to do the analysis that we're asking it to do. But we need to know how well it's doing, or how well it's performing, or how well it's actually doing something that we're asking it to do. Let's say we're talking about facial recognition. Well, if you're talking about facial recognition, a relatively high level of accuracy is probably required. If it was on your phone, you need sort of 80, 90, 100% accuracy. There's no point having a facial recognition system that doesn't recognize a face most of the time, especially if it's you and your phone and you can't get in because it doesn't recognize your face. However, if we're talking about facial recognition in a slightly broader context, where perhaps a police force is analyzing a crowd, then we need to start talking about a lower level of accuracy, so you can scan a wider number and get a wider number of hits, and then the human person can be involved in saying, yes, this person matches what we're looking for, or this person doesn't. I'm obviously avoiding the morality and the moral suggestions that such a facial recognition model would bring about. I'm just using it purely for a discussive purpose here. Once you've worked out what your targets are, you then need to have a plan to recognize drift and retraining. And again, we'll talk about that a little bit more as we go further through. But the general premise is that as a data science model goes through its lifespan and gets older and older, it's likely to be less accurate and needs to go through a period of retraining. So understanding how that operates and how that will impact in your data science model is a critical element as well. And the last thing we need to be aware of is siloing. It is really, really, really easy in a data science project to end up in a position where we are siloing. It's a very, very real very real risk. And the reason it comes about is there's a bit of a mindset where a data scientist says, I'm going to build my model and then going to pass it to an engineer, and the engineer will integrate it. The engineer takes the model and integrates it, builds the front end, and then passes it to the QA. The QA has to test it and can only test it when both the model and the engineering piece are combined into a working system, and the QA is then able to test it and say, yes, this does, or this does not work. And in this way, it's really, really easy to end up in an isolated, siloed, agile approach, even though we're still operating under Agile Scrum, even though we're still doing estimations, even though we're all still doing sprinting, even though we're all still doing regular deliveries at the end. So it's very important to recognize that is a very real risk. And this approach also reduces the speed with which the value can be delivered quite dramatically.